Okay, welcome everybody. This is our last Pohle Colloquium for this school year. I was a little bit uncertain about the fall, but going forward now, I think you should definitely plan on a usual fall schedule for the Pohle Colloquium. That is first Wednesday of October and November, and possibly December, depending on the weather and the Farmer's Almanac and all of those important sources. And as always, if you have any suggestions of people you'd like to hear speak, or if you happen to be at a conference this summer and you meet someone that would like to talk, put them in contact with me. Today we are very, very happy to have Bill Dunham. Now, some of you may remember Bill Dunham as a named professor from Muhlenberg College who gave spectacularly good talks in the history of mathematics. Bill is now a research associate at Bryn Mawr College who gives spectacularly good talks in the history of mathematics. And given that Bill is at Bryn Mawr, he actually suggested a couple of talks today that he could have given about the history of mathematics at Bryn Mawr, and even one that involved a guy called Russell. Bertrand Russell, is that his name?
Yeah.
Of course. But I convinced I convinced Bill to give an internalist talk, preferably about Euler, in large part because we lost Ed Sandifer this year. Many of you remember Ed Sandifer. And he'd been sick for a while, but he died on August 31st of 2022. I really thought it would be nice to have a talk with the sort of things that Ed loved, internalist details, and preferably the topic of Leonhard Euler. So Bill has come here to tell us an Eulerian tale of two series, and we're doing this in honor of Ed Sandifer. Thanks very much, Bill.
No, thank you. Pleasure to be back here and to dedicate this to Ed. This will be done in his spirit, although without his jokes, the groaners. So Euler, I want to talk about Euler. This is Euler, the famous picture where you can see why he did not become an international icon of fashion. It's very clear that he was not going to the Met Gala, with that outfit, but that's what he wore. If you do Euler, you could do number theory, you could do differential equations, there's all sorts of topics. I mean, just this side of an infinitude of topics I think you could do. What I'm going to do is look at two infinite series that he summed. And Euler had this ability, I would call it uncanny, if not supernatural, of being able to get exact values for infinite series which seem impossible to do exactly. So I have two of these I want to show you and see what you think. I'm impressed. So the first one, this is 1773. It's this series. Tangent of pi over 4 plus half the tangent of pi over 8 plus a quarter the tangent of pi over 16. I think you see the pattern. And 8 the tangent of pi over 32, etc. The pattern's quite clear and quite simple. 1 over 2 to the n tangent of pi over 2 to the n plus 2, it's just that. Infinite series, and what happens to this thing? So the question is, does it converge? Mm-hmm. If so, can you bound it? Yeah, let's see. There's the series. Now, we could show this converges via the comparison test. You could actually use this in a calculus class. This is not that hard. All the terms are positive because of the nature of tangent. And of course, the tangent of pi over 4 is 1, which is convenient. And then, because the tangent's increasing, the tangent of pi over 8 is less than the tangent of pi over 4, and hence less than 1. And the tangent of pi over 16 is less than 1. And all those tangents are actually less than 1. And there's your comparison. Because the series that Euler is looking at, tangent pi over 4 plus half tangent pi over 8, and so on, is less than just 1 plus a half times 1 plus a fourth times 1. And that, your calculus students recognize, is a geometric series which converges to 1 over 1 minus a half, or 2. So because the larger series converges, this one does, this converges, it's bounded above by 2. So that's that second question, can I find bounds? Well, can't be bigger than 2. And what's a lower bound? Well, what if I just took the first term and say that whatever this is comes out somewhere between 1 and 2. So there is an answer, it's between 1 and 2. But That's not what Euler wanted to know. He said, I have a more ambitious issue. I want to figure out what exactly this sums to. And that one is not so easy. What in the world does this add up to exactly? So this is what Euler is going to attack. Now, I should say that whenever I asked this question, how, I had an idea. So I thought, I don't need Euler. I'm going to do this myself. So here's my idea. The tangent of pi over 4 is 1. So it looks like a trig series, but I could just get rid of that first term and make it 1. But in fact, I can get rid of all those tangents and turn them into numbers if I remember some trig identities. So this is going to be my approach. So with some trig identities, I claim I can convert all of those tangents into numbers, things called quadratic surds. There's going to be lots of square roots in them. And those are the identities I need. Now, I confess I didn't actually remember these right off the top of my head, but once I saw them, I said, yeah, I get it, that the cosine x is the square root of 1 plus cosine 2x over 2, and the sine of x is the square root of 1 minus cosine 2x over 2. And you don't need the plus or minus in front of the roots for the things we're doing, because tangents of pi over 4, pi over 8, pi over 16, everybody's positive, so we'll just go with the square roots without the plus minus in front of it. Now, if I know that I know what the cosine of pi over 4 is, this identity lets me figure out what the cosine of pi over 8 is. Because the cosine of pi over 4 is square root of 2 over 2. You stick that in there, and you find out that the cosine of pi over 8 is exactly the square root of 2 plus the square root of 2 over 2. I might have known that once, but I recovered it. Likewise, the sine of pi over 8, using the identity up on the right, replacing, the cosine of 2 pi over 8 is the cosine of pi over 4. Out it goes, and that is the square root of 2 minus the square root of 2 over 2, and hence the tangent of pi over 8, which is one of the terms in my series, is the quotient of sine over cosine, which is this square root over that square root. The 2's cancel, and there you go. That's the exact value of the tangent of pi over 8, the square root of 2 minus root 2 over the square root of 2 plus root 2. So now I can replace that trig function, that trig expression, with the exact value. And no use stopping there. Suppose I want to move it to the next one. The cosine of pi over 16, well, it involves the cosine of pi over 8, and I just did that. I'm backing up. There it is. There's the cosine of pi over 8, so I put that in. Likewise, the sine of pi over 16, I put in what the cosine of pi over 8 is, and I get the tangent is the quotient. And as everyone can see, that comes out to be the square root of 2 minus the square root of 2 plus the square root of 2 over the square root of 2 plus the square root of 2 plus the square root of 2. And so that's the tangent of pi over 16. And then you can do the tangent of pi over 32. And thus take this terrible trig series and replace it by the far easier exact numerical series. It starts with this, and the next term is that. And the next term has more square roots. And those are exactly the same. But this was my idea of doing the problem, not Euler's. Because, the reaction to this should be Edvard Munch, right? This is impossible, right? Nobody wants to do this. So, okay, my idea was lousy. So let me show you Euler's idea, what he did. He said, no, all I need is this trig identity, that the sine of 2x is 2 sine x cosine x. And if you know that identity, which everybody does, and if you have a 4-digit IQ like Euler, you can put it together and sum the series in question. Because he says this, let's take the sine of theta. Now I can use that identity up there and write that as 2 sine theta over 2 cosine theta over 2. Okay, but look at that, sine of theta over 2. I can use the identity again. It's got the right form. And so that becomes 2 sine theta over 4 cosine theta over 4 in the square brackets. You still got the 2 out front. You still got this cosine of theta over 2 hanging. If I multiply the 2's, I get that the sine of theta is 4 sine theta over 4 cosine theta over 4 cosine theta over 2. And now you attack the sine theta over 4 with the identity again. So he goes back up there, and this now becomes 4 times 2 is 8 sine theta over 8 cosine theta over 8. then there's the cosine theta over 4, then there's the cosine theta over 2. So the product is expanding, and now you do it to the sine of theta over 8, and you get to sine theta over 16, cosine theta over 16, etc. And Euler says, do it forever. Forever. And he says, what you'll get then is the sine of theta is, now over on the right, you got all these cosines, and I'm going to turn them around so that they're descending in the angles instead of ascending here. So you got the cosine theta over 2, the cosine theta over 4, the cosine theta over 8, dot, dot, dot. And then what happens out front here? You know, the next one will be 16 sine theta over 16, and then there'll be a 32 sine theta over 32. Well, he says if you do this forever, what you get is n sine theta over n, where n is an infinite number. So this is what he says. So n is infinity. So infinity sine theta over infinity. Now, why didn't he just do the limit? Well, they didn't have limits in the 18th century, so he's working pre-limit, and so this is how it comes out. So here's where he is, and he goes on and says a little more. He says, because n is an infinite number, n sine theta over n is theta. So he makes this observation. Now, I'll go back and check, make sure I believe this, but if we go with that, then I can take away the n sine theta over n. See, I got all those cosines there on the right. I got sine theta on the left, but where n sine theta over n is, because n's an infinite number, you just put theta. And so this is the identity that's going to propel him to summing the series with all those tangents in it in about 10 minutes when we get to it. So we're not there yet, but we're working toward it. Now, the trick was to replace n sine theta over n with theta, and we would say what this is a limit as n goes to infinity. We're getting an infinite product over there. We're going to take a limit, and just to be sure we believe this, what is that? The limit n goes to infinity of n sine theta over n. Well, calculus students can do this. Here's what I did. I let x be 1 over n, just to get an x in there. And that means n is 1 over x. And as n goes to infinity, becoming an infinite number, the x goes to 0. And so what Euler was looking at in our parlance, this limit, is the limit as x goes to 0 of sine, instead of theta over n, it's sine theta x. And then this n up here becomes an x on the bottom. So that's really what's up. As x goes to 0, sine's continuous, so the top goes to sine of 0, the bottom goes to 0, and voila, L'Hopital's rule. So that is lurking behind this. And L'Hopital's rule says take the derivative top and bottom, derivative of the top, theta sine theta x, derivative on the bottom 1. Take the limit of that, and you're not going to get 0 over 0, that's for sure. You got a 1 down here. Up above, you get theta times cosine of 0, which is theta. So, of course, Euler's right, that whenever I have this thing with an infinite number here, I could just take out that front end and replace it with theta. So Euler didn't have the terminology maybe, but that's all right. He knew what he was doing. Okay, so there's the identity that's going to be critical. Now, at this point, I'm going to solve for theta. So if I do that, I divide the sine by all those cosines, and that will be theta. So Euler writes this down. And then he says, the angle itself can be very beautifully expressed by its sine and the cosines of angles continually diminished in double ratio. So he's rather impressed with this result. The angle here, theta, is expressed in terms of the sine of theta on top and all these cosines where the angles are continually diminished in double ratio. That's remarkable, right? Because you can use this to go from the sine of theta to theta without using inverse trig functions. So you know, suppose someone gives you that sine of theta is 0.8. What's theta? Okay, that's the challenge. So you say, well, I can do that. I get out my calculator, I push arc sine of 0.8, but my button is stuck. I can't, it doesn't work. I can't use the arc sine function. Now what? You use Euler's little formula, and you can do an arc sine without an arc sine, just with the sine. You don't need the inverse function to invert it. Because if the sine of theta is 0.8, then the cosine of theta is the square root of 1 minus sine squared theta, which comes out to be 0.6. And now I go back to this identity. The cosine of theta over 2 is 1 plus cosine theta over 2, the identity I had up before. 1 plus 0.6 over 2 is 0.8. Square root of 0.8, you get 0.8944. That's the cosine of theta over 2. What's the cosine of theta over 4? Use the identity again. But now where this cosine is, you put 0.8944, add 1, divide by 2, take the square root, 9732. And I did a couple more of these. Cosine theta over 8 is 0.9933. Cosine theta over 16 is 0.9983. Cosine theta over 2 is 0.9996. And I got tired of it. So there's a bunch of cosines stemming from that sign. OK, now we go back to Euler's little formula. This one, which he thought was pretty cool. Because now what I can do is substitute up on top theta, sine of theta was 0.8, and the bottom's an infinite product, so I'm not going to put an infinite number of terms here, so I put a squiggly equal, an approximate. But the cosine of theta over 2, we said, is 0.8944, and the cosine of theta over 4, theta over 8, theta over 16, theta over 32, just numbers. Those buttons work on my calculator, so I punch those in, and out comes 0.9272. So what I've just shown is, if the sine of theta is 0.8, theta is about 0.9272. And I only used the direct trig functions, not the inverse. Somebody brings me a new calculator. It works. So now I can do this the old way, or the easy way. Sine of theta is 0.8. Theta is arc sine of 0.8. Guess what? That's 0.9273. So, of course, it's very close. So this is sort of amazing. You can invert a trig function without leaving the realm of the direct trig function. You know, if I tell you the log of x is 0.8, what's x? Oh, it's e to the 0.8. But no, the e button doesn't work. You can only use logs to invert logs. What are the chances of that? I don't know. I mean, but this one comes out rather nicely. So when Euler said the angle itself can be very beautifully expressed by its sine and the cosines of angles continually diminished in double ratio, he was right. That is pretty neat. But it has nothing to do with my series. I mean, I'm just babbling here. So let's get back to the series, which we're trying to sum, which was tangent of pi over 4 plus 1/2 tangent of pi over 8. It's actually got a lot to do with this, but let's see. What do? I look at what Euler has here. One thing strikes me right away. It's a cool identity, but there's no series. Right? This is nothing's added up here, so that's not very good. So the question is, how do you turn a product into a sum? Well, Euler always knew how to do this. You take logs. So he's going to take logs of this. That turns products into sums. Now, the rule usually is for finite quantities. The log of AB is log A plus log B, and here we have an infinitude. It never bothered him, so just do it. So I take logs, and I get log of theta on the left. I get the log of sine theta minus the log of cosine theta over 2 minus the log of cosine theta over 4, etc. An infinite series. However, that's a wash in logarithms, right? That's definitely not cool. Too many logarithms. So the question is, how do you get rid of logs? Well, you could exponentiate, but that's not going to work because you'll be right back where you started from. You just undo it. Now, he has a better way. He had a cooler way to get rid of logs. Differentiate. So now we're going to enter the realm of calculus. Take the derivative of log theta, and you get 1 over theta. The derivative of log sine theta is what? 1 over sine theta times cosine. He remembered the chain rule, and this is good. The derivative of minus log cosine theta over 2 is minus, and then you get the cosine theta over 2 here and minus 1/2 sine theta there. The next one will be minus 1/4 sine theta over 4 over cosine theta over 4 forever, taking the derivative all the way down. There's 1 over theta. Cosine over sine is cotangent. Minus minus is plus 1/2 tangent of theta over 2 plus 1/4 tangent of theta over 4 plus 1/8 tangent of theta over 8. This is starting to look promising here. Not quite there yet, but there it is. All right. So now the original one had tangent of pi over 4 and half tangent pi over 8 and so on. So it seems like we better let theta be pi over 4 to fit the pattern. So on the left you have 1 over pi over 4. Over there you got cosine pi over 4 plus half the tangent of pi over 8. Yep, that's what I wanted. A quarter tangent of pi over 16. Yep, that's what I wanted. Everything's kind of lining up here. I guess if I don't like fractions within fractions, we'll just flip that and make that 4 over pi. So everything's good except this isn't supposed to be cotangent of pi over 4. It's supposed to be tangent of pi over 4. So we remember that the cotangent of pi over 4 is 1. And then I remember that the tangent of pi over 4 is 1 too. And so it really was, right? There it is. That's the answer. The series he gave sums exactly to 4 over pi. I would not have guessed this. 4 over pi is the exact value of this thing. Notice that 4 over pi is between 1 and 2. We had bounded it properly. But, of course, rather than supply an approximation, Euler found the exact value in an amazing argument, I think. He actually did it another way in this article. One way to do it wasn't good enough. He wanted another way, and I'm not going to do it another way, but this will be left as an exercise. If you want to try it a completely different way to get the same answer, he said you need this identity, which is even less familiar to me, but the tangent of theta is the cotangent of theta minus twice the cotangent of 2 theta. And if you apply that to all those tangents, replacing them with cotangents via this identity, what you'll find is you'll get a telescoping series. And you end up not with an infinite series, but just 2 terms, the first term and the last term, but the last term is going to involve an infinite number. Then you got to go clean up that and figure out what that is using L'Hopital's rule. And when you're all done, 4 over pi emerges. So he actually could do this 2 different ways, quite different. Okay, so that's my first series. Now, the second series differs from the first in multiple ways. It's not trigonometric. And the first series was very clear what the pattern was. It wasn't clear what the answer was, but you could see what each term was going to be. The second series does not have that property, as you'll see in a minute. Now, before I plunge into it, I'm going to need 2 prerequisites, so let's just remember these. The first one is the Leibniz series from 1674, which Euler certainly knew, and it's this one. 1 minus a third plus a fifth minus a seventh plus a ninth, the alternating series with odd denominators. Notice if the denominator is 1 more than a multiple of 4, 1 more than a multiple of 4, you got a plus in front of it. So 5 has a plus in front of it, 9 has a plus in front of it, 13 has a plus in front of it. If it's 1 less than a multiple of 4, it's got the minus a third, minus a seventh. And Leibniz showed that this adds up, converges to pi over 4. He was not the first person to do this. He kind of thought it was very good. He patted himself on the back. He got credit for it in most books. We call it the Leibniz series. Good enough. So we're going to need that. The other one we're going to need is the Basel problem, which was done by our friend, the fashionista here, Euler. And that one doesn't have any alternating series at all. It's the sum of the reciprocals of the squares, 1 plus a fourth plus a ninth. And in 1734, he showed, in what is still a breathtaking result, that this is pi squared over 6. It's got to be one of the great, great, great formulas of all. Okay, so these are going to be the 2 pieces we're going to need to do the series, which I haven't shown you yet, but keep these in mind. We'll see them again. All right, what's the series? Well, I'm writing down this string of numbers. 1, a half, a third, a fourth, a fifth. Yes, believe it or not, I went all the way up to 1/25. This was great fun typing this. It's just the reciprocals of the whole numbers. Okay, now, suppose we put plus signs in front of everybody. 1 plus a half plus a third plus a fourth, all the way. Well, then that, of course, is called the harmonic series, and of course, we know it diverges. Euler knew it diverges. Mengoli knew it diverged, or Rem knew it diverged. People knew this had diverged. So, okay, put all plus signs, infinity, which is kind of amazing, too, if you think about it, because the terms are melting away to nothing, and yet the sum grows beyond any bound. All right, so that's not the series. So there's my reciprocals again. Suppose this time I decide to play a different game of putting the signs in. I'm going to alternate them. 1 minus a half plus a third minus a fourth. Flip-flop, back and forth, back and forth. Now that one you've seen, and if you've taken calculus, that's called the alternating harmonic series. And this time, it converges. Conditionally, as we would say. And actually, we know what it converges to, log 2. The idea is that there's all these positive pieces, the 1 and a third and a fifth, kind of blowing up toward infinity, but then there's all these negative pieces pulling it back, and somehow in the end, it converges. There's enough positives and negatives working against each other that we get a finite answer. Okay. Well, now I'm going to show you Euler's series. I start with the same stuff, the reciprocals of the whole numbers. So he says, here we go. 1 plus a half, plus a third, plus a fourth. Oh, looks like the harmonic series. No, minus a fifth. Okay. Plus a sixth, plus a seventh, plus an eighth, plus a ninth, minus a tenth. Plus an 11th, plus a 12th. Okay, I think I see it. Every fifth term, he negates it, right? Nope, next one's minus a 13th. Okay. Then it starts alternating. Plus a 14th, minus a 15th, plus a 16th, minus a 17th, plus an 18th. So this should be minus a 19th, right? Nope, that's a plus. This is getting mysterious here. The 20th, what am I going to guess on this one? Hey, the 5th was negative, 10 was negative, 15 was negative. I'm going to say 20 is negative. It is, so that's negative, okay. Then the next 4 are all positive. And now we're getting the 125th. Should be negative, right? Multiple of 5. Nope, that one's plus. But 126 is negative. And then the remaining few, the next few are plus a 27th, plus a 28th, minus a 29th, minus a 30th, plus a 31st. And I'm going to call this E for Euler's series. This is what he wants to attack. Now, the first question that anybody should ask is, where in the heck are these signs coming from? How do you know what the next term is? What's the sign in front of 132nd? What's the sign in front of 320th? How in the world are we determining these things? It looks haphazard. It looks random. But there's a rule. So my first question is, how are the signs generated? And rather quickly, you come to realize that the issue is, look at the denominators are the ones with the negatives in them. Those are kind of the special ones. 5, 10, 13, 15, 17, 20. What common property do these numbers have that would account for that minus in front of them? So try to determine or identify those denominators preceded by minus signs. There's the first few. What do those have in common that all the other numbers in the universe do not? Well, if I gave you this problem and you had a week, you'd figure it out, or maybe a day, or maybe an hour, or you could go to the Encyclopedia of Integer Sequences online, where you type in a sequence and it tells you where it's coming from. I guess everybody knows about this. It's really amazing. Somebody did a lot of work to generate these. Well, sure enough, this one's in there. I typed in 5, 10, 13, 15, 17, and the online Encyclopedia of Integer Sequences, this is known by the familiar result, A209922. And so you look up A209922, and it tells you where these are coming from. Now, Euler didn't need to type in anything into the online Encyclopedia of Integer Sequences. He knew where they were coming from, but I didn't. Here's the rule. You take the number n in this string, factor it into primes, and then include n in the sequence if and only if its prime factorization contains an odd number of primes that are one more than a multiple of 4. That's what's determining this. So every odd prime is either one more than a multiple of 4 or one less. So that's either a 4k plus 1 prime or a 4k minus 1 prime. And so you factor the number, look for all the 4k plus 1 primes, count them. If it's an odd number, that number belongs in the list. If it's an even number of these 4k plus 1 primes, it doesn't get in. And you don't care about the 4k minus 1 primes or 2, which is an even prime. You can have as many of those as you want. That won't affect anything. All that matters is, do you have an odd number of 4k plus 1 primes? And all of these have that property, an odd number of 4k plus 1 primes in their factorization. Now, suppose I said, what sign should precede 1/90th? You know, if you go out here far enough, you're going to come to 1/90th. What goes in front of it? Well, according to the rule, you factor 90 into primes, 2 times 3 times 3 times 5. Only one of them is a 4k plus 1 prime. 5, 1, that's odd, so that gets a minus. The next number up, 191, 191st, what sign does that have? Well, that factors into 7 times 13. That's a 4k minus 1 prime. There's a 4k plus 1 prime. There's one of them, minus. What about 1 over 260? This is the last one I'm going to do, I promise. 260 factors into 2 times 2 times 5 times 13. What sign? That's a 4k plus 1 prime. That's a 4k plus 1 prime. There's two of them, even number, plus. And so that's where this series is coming from. That's how the signs are allotted. Complicated. Look at that number. What sign precedes 1 over 3,333,333,333,337? Now, just think about this. If instead of Euler's series, I'm looking at the Leibniz series, that first one we saw. 1 minus a third plus a fifth minus a seventh. This is easy in the Leibniz series because that number is 1 more than a multiple of 4. Because if it ended in 36, that would be a multiple of 4. So for the Leibniz series, this has a plus in front of it. Easy, easy, easy. For the Euler series, you would have to factor this into primes. Good luck with that. And then count how many of them are the 4k plus 1 kind, how many are the other. And if there's an odd number of 4k plus 1, you get a minus, otherwise a plus. That would drive anybody nuts, right? And it would drive me nuts because I started screaming again when I thought about that. Now, maybe a computer could factor that, but I could write down a denominator that had 1 billion digits, and no computer on earth could factor that into primes and determine what sign actually goes in front of that term. It would be impossible with modern technology to actually write down 1 billion terms of Euler's series. So it seems hopeless that you could ever do anything with this. I mean, you can hardly even know where it's going. So you ask a question like this: is it converge or diverge? You know, it seems I can't answer it. What I could do is find some partial sums. Maybe that would help. So that's what I did. So my first question is, where are the signs coming from? Okay, I figured that out, or Euler did, or the online encyclopedia did. Second question, can converge or diverge? Well, if I added up the first 100 terms of this, and it came out to be 2.93. That doesn't prove anything, but it's instructive. Then I had a very long, rainy afternoon, and I added up the first 200 of this by hand, with my calculator. And I got 3.37, so it had grown. Then I called my friends at the online encyclopedia of integer sequences and said, hey, can you add up 20,000 terms of this? And they could. And they told me that if you added up 20,000 terms, you get 3.12. So now it's sort of coming back down. That gives me some hope that maybe it's going to converge. That's not a proof, but maybe. And that number looks suspicious, 3.1. I've seen a number like that. So. Okay, so now, here comes Euler's genius. He actually sums it. The series that you cannot even write down all the terms of, he sums it. And he does it in a stroke of genius that prompted me to do a cartoon. So this is my only cartoon. There's Euler, and there he is, so you're getting the idea. And I'm going to do it again, once more, because it takes a long time to make one of these there. Okay, so Euler had an idea. His idea involved 3 steps only. So let me show you the 3 steps, and when we're done, the answer falls out. Step 1, he goes back to the Leibniz series. Remember I said we're going to need this. Pi over 4 is 1 minus a third plus a fifth minus a seventh. That's an infinite sum. He says multiply everything by a third all the way across. So a third of pi over 4 is a third minus a ninth plus a 15th minus a 21st. Just everything gets hit with a 3. Draw a line and add. Add them up. And look what happens. The minus 1/3 here cancels the plus 1/3. The plus a ninth will get wiped out by the minus 1/9. All of these signs are different below than they were above, so those are all disappearing when you add. And those are all the multiples of 3. They're gone. So when I add on the left, I get pi over 4 plus a third of pi over 4. He writes it this way, 1 plus a third times pi over 4. On the right, no more multiples of 3 in the denominator. So you get 1 plus a fifth minus a seventh, the ninth's gone, the 15th is gone, the 21st is gone. So you got that. Okay, now what? Well, he now attacks this 1/5. He wants to get rid of a fifth and all the multiples of a fifth. So why not multiply both sides by a fifth? So over here we put the fifth out in front. And on the right, you get a fifth plus a 25th minus a 35th. Draw the line. This time I can't add. Because if you add, you got a fifth there and a fifth there. That's not what you want to do. You want to subtract to get rid of this. So now you subtract. Notice up here, there would have been a plus 1/25th in the Leibniz series. And here's a plus 1/25th, so when you subtract, that'll be gone. There would have been a minus 1/35th. Here's a minus, subtract, it'll be gone. So he draws the line and subtracts, and now he says on the left, you get 1 minus a fifth, 1 minus a fifth of this, 1 plus a third times pi over 4. And over there, you got what looks like the Leibniz series where it's been stripped out of all of its multiples of 3 and all of its multiples of 5. So there we are. And now you do it for the 7th. When I do it for the 7th, I'm going to add. Right? Whenever I do this line down here, it's going to have a plus a 7th. I'm going to add. With the 11th, it's going to have a plus down below. I'll add. But with the 13th, I'm going to have to subtract. So sometimes you add and sometimes you subtract. And here's what emerges. The first few terms. You got the pi over 4. I guess I moved it to the left here. It's first. I inverted the order here. 1 plus a third, 1 minus a fifth, 1 plus a seventh. And notice that the denominators with a minus in front of it are the primes of the form 4k plus 1. And the denominators with the plus in front of it are the other family, the 4k minus 1. So this is segregating them into pieces, and those signs are going to be critical here. All right, so there's where we are. And then Euler hits both sides with a 4 over pi, and he gets this product, that 1 plus a third times 1 minus a fifth times 1 plus a seventh times 1 plus an 11th is 4 over pi. And as I was putting this together, I noticed that's the answer to the first series, 4 over pi, but that's just coincidence. That has nothing to do with this. So there's his first piece of the puzzle. He turned an infinite series, the Leibniz series, into an infinite product. Second step. He's going to turn an infinite product into an infinite series. The guy was nothing if not agile, right? Fluid. He could do it either way. So this time he starts with this infinite product. 1 over 1 minus a fourth times 1 over 1 minus a ninth times 1 over 1 minus a 25th. Notice these are the primes squared. 1 over 1 minus 1 over p squared for all the primes, including 2. 2 squared is 4, 3 squared, 5 squared. Okay. So that's an infinite product. Now he recognizes each of these terms, each of these factors, as the sum of an infinite geometric series. You know, if you got the series, 1 plus r squared and so on, we usually get the simple sum 1 over 1 minus r. But there's no reason you couldn't start with 1 over 1 minus r and expand it the other way as a series. So 1 over 1 minus a fourth is just 1 plus a fourth plus a 16th plus a 64th, all the powers of 4 here. 1 over 1 minus a ninth is 1 plus a ninth plus an 81st, infinite series. 1 plus a 25th plus a 625th, 49th, 121. We turn each of these fractions here into a series. And now Euler says multiply them together. You know, infinitely many, infinite series, we're going to multiply them together. But we can do that, sort of. When you multiply these, each paren contributes one term in the product. So I'm going to get a 1 times a 1 times a 1 times a 1. I'm going to start with a 1. This 1/4 will hit all the other ones, so I'll get a fourth. So it's going to start 1 plus a fourth. This 1/9 will hit all the other ones, and I'll get a ninth. 1 plus a fourth plus a ninth. Plus a 16th, when this hits all the other ones. Plus a 25th. Oh, this is looking good. 1 plus a fourth plus a ninth plus a 16th plus a 25th. The next square up would be 36th. Do I get a 36th out of this? Yeah, 4 times 9. There we go. There goes the 36. 6, after all, is 2 times 3. And you square it, you have 2 squared times 3 squared. And so a 36th will come out. A 49th will come out. There it is. A 64th will come out. An 81st will come out. A 100th? Sure. 100 is 4 times 25. These two will multiply. And so if you convince yourself, think about this a bit, you see this is going to expand to be the sum of the reciprocals of the squares. Any square is going to have to be built up of primes to even powers, and there they all are. And at some point, they're going to multiply together to give you that square. And it can only happen one way, by unique factorization. There's not another way to get 1/25th other than 1/100th other than 4 times 25 in terms of the primes. So when you take this bizarro product up here, convert it into a series, you get this series, and he knows that series because he, of course, summed it, and that's pi squared over 6. So that's kind of amazing in and of itself. This product becomes pi squared over 6. There it is. And then what he wants to do is take reciprocals of everything, flip them all over, and so you'll get 1 minus a fourth times 1 minus a ninth times 1 minus a 25th is 6 over pi squared when you flip that over. And that's the second piece of the puzzle, to sum the series E, which is so complicated. Last step, final step. He says, there's what we did first, 1 plus a third times 1 minus a fifth times 1 plus a seventh is 4 over pi. Here's what we did second, 1 minus a fourth times 1 minus a ninth, etc., is 6 over pi squared. What do? He says, just divide the top one by the bottom one. Just divide. And so you'll get this mess, right? The numerator here is that term, and that equals 4 over pi. And the denominator down here is this guy, which equals 6 over pi squared. So you divide your two steps and hope for something good to happen. Well, the right side's easy, so we're going to abandon the right side for a minute. The left side's where the battle is waged. So let's look at the left-hand side. What do you do with that? Maybe it's time for a scream from Edvard Munch again, but not really, because these denominators are differences of squares. 1 minus a fourth, 1 minus a ninth, factor them. So you leave the top alone, 1 plus a third, 1 minus a fifth, and so on. But down here, 1 minus a fourth is 1 plus a half times 1 minus a half. 1 minus a ninth is 1 plus a third, 1 minus a third, 1 plus a fifth, 1 minus a fifth. And now, cancellation is going to happen, because these things on the top have counterparts below. So you take the 1 plus a third and wipe out that one. You take the 1 minus a fifth and wipe out the 1 minus a fifth. It's a different piece that got wiped out. The 1 plus a seventh takes the 1 plus a seventh, the 1 plus an 11th, 1 minus 13th. You do all that cancellation. The numerator is going to be a 1, and the denominator is going to be whatever detritus is left down here. So you get 1 on the top. 1 plus a half, I'm going to write that as 3 halves. But all the other terms are 1 minus a half, 1 minus a third, 1 plus a fifth, 1 minus a seventh, 1 minus 11th, 1 plus a 13th. And notice that you got the plus sign here for the 4k plus 1 primes, and the minus for everybody else. That could be significant. Right? All right, so there's where we are. Let me put that up on top. How about we do this? We break it. Instead of this 3 halves on the bottom, we write it as 2/3. We take this second chunk and write it as 1 over 1 minus a half, 1 over 1 minus a third, 1 over 1 plus a fifth, etc. And now, use Euler's trick again. Take each of these and convert it into a geometric series converging to that. So now we pull the geometric series back. So the 2/3 is waiting in the wings here. 1 over 1 minus a half is 1 plus a half plus a fourth plus a 16th. 1 over 1 minus a third is 1 plus a third plus a ninth plus a 27th. But 1 over 1 plus a fifth has got to be an alternating geometric series to come out right. 1 minus a fifth plus a 25th minus a 1/25th. The next one will be 1 plus a 7th plus a 49th, 1 plus an 11th plus a 1/21st. And here comes another alternating one. 1 minus a 13th plus a 1/69th. And you notice the alternating ones are going to be the ones that are attached to the 4k plus 1 primes. All right, so that's the left-hand side, and I got to do something with it. So there it is again. And now I multiply it out. Whoops, I should have not done that yet. The 2/3 will be here. I'm going to multiply it out. You're going to get a 1. 1 times 1 times 1. So it's going to have a 1 in it. It's going to have plus a half when that hits all the other ones, plus a third when that 1/3 hits all the other ones, plus a fourth, minus a fifth, plus a sixth. Can you see it? Plus a sixth. The half times a third. There's the sixth. Plus a seventh. There it is. Plus an eighth. Plus a ninth. Minus a tenth. Because a tenth is 5 times 2. And there's a plus and minus. 1 negative, 1 positive. Plus an 11th. Plus a 12th. Plus a 12th. Yeah, that's 4 times 3. Yeah. Minus a 13th. You expand this and you realize what you're getting is Euler's series. It's working just like the rule. If you have an odd number of 4k plus 1 primes, you're going to get a minus out of this because of this flip-flopping. But if you have an even number of 4k plus 1 primes, like with 1/25th, that came from a positive term because you had to alternate back there. So this is, in fact, 2/3 of E when I did all this. The left-hand side is 2/3 of Euler's Bizarro series. So all that remains, remember we had this thing, the left side we collapsed to 2/3 of E. All I got to do is figure out the right side, and this one even I could do without needing Euler because it's 4 over pi divided by 6 over pi squared, which is 4 over pi times pi squared over 6, which is 2/3 of pi. That's the right side. And so the left side equals the right side. The left side was 2/3 of Euler's series. The right side is 2/3 of pi. Cancel the 2/3, and you get that Euler's series sums exactly to pi. This series, with the weird rule behind it, adds up to pi. And that seems to me to be quite miraculous, actually. It's amazing. That's pi. Now, if you think I'm lying about that, here's Euler's statement from the Introductio, where he does this. There it is, 1 plus a half plus a third minus a fifth. He writes out fewer terms than I did. He says the powers of 2 have a plus. Primes of the form 4m minus 1 have a plus. The primes of the form 4m plus 1 have the minus, and you just factor and count. And that determines the signage here. And so he did it, and the answer, pi. Now, this strikes me as so bizarre because the series has number theory, what do I say, baked into its very genes. You can't write this down without number theory to determine the signs, the factor into primes. That's number theory. But the answer is pi, which has geometry baked into its very genes because it's the ratio of a circle's circumference to diameter. And what on earth could the ratio of the circumference to the diameter of circle have to do with number theory like this? It doesn't compute, but there it is. So I'm impressed. I will leave you with 2 slides. One is from Ivor Grattan Guinness, who spoke at the Pohle once upon a time. And this is a famous line of his, but it's perfectly apt. He said, Euler was the high priest of sum worship, for he was cleverer than anyone else at inventing unorthodox methods of summation. And the 2 series I've shown you, I hope you agree, are very unorthodox in the method of summation. It's not what an ordinary person would ever think of, but Euler was the high priest. So I'll leave this with a shout out, way to go, Uncle Leonhard. Thanks. Yes, Joe.
So what was the context that Euler got interested in this series you call E, this number?
Well, truth be told, I suspect he didn't write down the series first and then sum it by this technique. But he was doing these products, 1 minus a third, 1 plus a fifth. He had stumbled upon those kinds of binomials multiplied together and realized that when they multiplied out, that'd be this. So I presented it, I'm sure, reverse order. But he was always looking for new formulas, new strange results, things, infinite products, infinite sums. And the fact that pi falls out of this one is amazing, it seems to me.
It's sort of vaguely related to his product sum formula, right? With what is it, the reciprocals of the...
The sum of the 1 over p's
Yeah, the sum of the
is
reciprocals
divergent,
of
is infinite, he said. Yeah, yeah. That was, again, he's playing games there, and with geometric series, as I recall how he does that. So yeah, so he has these things in his toolkit. You know, like if you ever want to get rid of logs, differentiate, and if you ever want to get rid of products, take logs, that sort of thing. And one of them was pull up a geometric series. If there isn't one, make there be one, and something good will happen. And so he's, you know, he inserted plenty of geometric series here. I shared this with Dick Gross, a number theorist at Harvard, and he said if this is not, that particular formula comes out of a more general theory of Dirichlet types and stuff. You know, the world has moved on so that Euler's sum can be rather quickly spotted today. But when Euler did it, no one had ever done anything like this. So this was blazing new ground.
Your final remarks, they sound a little mystical, and I appreciate that personally. Did people in this time draw any such, you know, conclusions that, oh my God, there's something going on here?
Well, depends how you define woo. But no, I think that they were certainly impressed, you know, with sort of the aesthetic beauty of something like this. I don't know that they would see this as foretelling the future or anything, you know, mystical like that. But maybe the great mystery is how Euler's mind worked, you know, that he could do something like this. And of course, this is just a drop in the bucket of what he did over his career. So many things that shouldn't be true, but they are, and it shouldn't be doable by a human being, but they were. He's quite something. Yeah.
Do we know anything about his personal life?
Oh yeah, he was well, he was Swiss. He lived in Russia for a while at the St. Petersburg Academy, in Berlin, and then back in Russia. So he did not much travel in his life. He married, and he had 13 children, and all but 5 of them, I think, died before adolescence, because this was the 18th century. He had a photographic memory. He was indefatigable. He was nice. All the stories are he was actually a nice person. You know, he would speak to the postman, you know, when they would buy good morning and that sort of thing. Not like Newton, who would never speak to anybody, but...
What with the children who did survive, what roads did they go down?
Well, one became a mathematician, right? Johann Albrecht Euler became a mathematician, but not up to his father's standard. The others, I don't know.
The other son was a military officer,
Ah.
I think. Yeah. And he has descendants here in the U.S. I think they've been fairly well documented.
Somebody once asked, he seemed like a nice guy, a smart guy. Was there any sin, you know, anything he did that is not admirable? And there was. He smoked like a chimney. That was the story. He was always smoking his pipe. So if you went in the room, it would be smoke everywhere. So, but we'll give him one little flaw like that, I guess.
He was very religious.
Yes, right. For which he, received some ridicule, right, in certain places for being too devout and too, Calvinist, I guess. Mm-hmm. But he stuck to his principles. Yes.
Go ahead, John.
When Ramanujan went to go under Hardy's tutelage, is there any indication that he was exposed to the methodologies and things?
I would suspect he was. That rings up a bell that Hardy said, if only Ramanujan had been born when Euler was alive. That those two could have been the greatest team ever, even more than Hardy and Littlewood, you know. This could have been the greatest team. They missed each other by centuries, but they have the same flavor, this, you know, almost mystical ability to see things that others can't see, to sum things that others couldn't sum. But I'm sure, especially when Hardy got him, Ramanujan saw these kinds of arguments and certainly benefited.
Any other questions? Well, let's thank Bill once again.
Thank you.